Hello. Let's start today's lecture by summary of what we have done till now. Okay, and we'll after the summary we'll take up some new things today. So here, let's summarize. Summary. So we have started these lectures by writing down first the D'Alembert principle. Okay, and that was MI RI double dot minus the forces other than the constant forces times the virtual displacements that are consistent with the constraints. Okay, that's what D'Alembert principle is. And then we went on to introduce generalized coordinates, and the reason was to transform this part into generalized coordinates, independent generalized coordinates, so I could equate the coefficient of dq alphas to 0. Okay, so I introduced generalized coordinates q of q's. Okay, so the set is q 3n minus k. Okay, that's good. Then we derived Euler-Lagrange equations, which are the equations of motion that describe the evolution of your system, and they were the following: del L over del Q alpha dot d over dt. Okay, that's the total time derivative, minus del L over del Q alpha. Let's say all the forces are obtainable from a scalar potential so that the forces are conservative. Again, then I can write this. Otherwise, on the right hand side you have generalized forces as well. Okay, that is good. Our Lagrangian is a function of generalized coordinates, generalized velocities. The time derivatives of q are called generalized velocities, and t also. Okay, let's make some observations now. Okay, so up to here what we have done till now, and we took some examples. Okay, so point number 1, note that these Euler-Lagrange equations, these equations are second order differential equations. Okay, so these equations I'm referring to Euler-Lagrange equations are second order differential equations. EQ, second order differential equation. Why are they second order? Let's look at here. The Lagrangian we wrote down last time. You remember we wrote down last time the most general form of kinetic energy function, the T. Okay, and we saw that it has a T0, T1 and T2. Okay, T2 is quadratic in the generalized velocities. So your Lagrangian, which is T minus U, will have quadratic terms. Then when you take a partial derivative here, this piece, with respect to one of the generalized velocities. Okay, you take the quadratic function and you take a partial derivative with one of the velocities. You'll be left with a function which will be linear in the generalized velocity. Okay, and then when you take the time derivative, you will generate the second order differential of q, the second order time derivative of q, and that's why these equations are second order differential equations. Let me write it down here. Since the kinetic energy function T, okay, that is what we have been calling it, is quadratic in q alpha dots. Okay, you remember you have terms like q alpha dot, q beta dot, time a function which is a function of the q's. Okay, this is what we discussed, I think, in the last video. Okay, because of this and taking a time derivative, taking a partial derivative with respect to q alpha dot of t, which is the part of Lagrangian, will generate a linear term in alpha dot. Linear terms in terms which are linear in q alpha dot. Okay, and then when you take the d over dt, which is here, you will be taking d over dt of this guy, which is nothing but q alpha double dot. Okay, so you see that your equations of motion are second order differential equations, which you already know that they should be. Also note a very important property here, that in writing down these equations of motion, the Euler-Lagrange equations of motion, these ones, okay, we never appealed to any special property of the generalized coordinates. Okay, there was nothing special about the coordinates which gave us this form. If instead of choosing q alpha, we had chosen some other set, q alpha prime, we would have still gotten the same form of the Lagrange equations, Euler-Lagrange equations, right? We would still have gotten this. Okay, which means that the form of the Euler-Lagrange equations is independent of the choice of generalized coordinates that you make. Okay, which is quite clear from our procedure. We never appeal to any special property of the q's. And more precise, let me write it down. Maybe write it down on next sheet. The form of Euler-Lagrange equations is independent of the choice of generalized coordinates. That's quite evident statement. Okay, nevertheless, let me write down what it means mathematically. It means that if you had chosen, instead of the q's, q primes, okay, I'm making a shorthand notation. Instead of writing q1, q2, so forth, I'm just writing q. If we had chosen this, then still you are going to get the following, okay, sorry, del over del q alpha prime dot, okay, d over dt minus del L over del q alpha prime equals 0. That's what you would have gotten. Okay, where you know your Lagrangian is the kinetic energy minus potential energy. Take L in terms of R and T, the Cartesian ones, convert them to the generalized coordinates Q or the Q prime. So all these three L's are the same, and that's what you see here. So let me put L prime here. Okay, so what I'm saying is your L prime Q prime dot T is same as L Q dot T, right? These are the same functions. So that's what I mean by saying that the equations, the form of equations is independent of the choice of the generalized coordinates. Okay, that's one important thing. Okay. Okay, let's see what I should say. Okay. Maybe to the next video, to the next slide. Okay. Now let's say you are studying some system and you have set up the Lagrangian for that system, and you discover that not all coordinates appear in the Lagrangian. Okay. Those coordinates which do not appear in the Lagrangian are called cyclic coordinates or ignorable coordinates. And there is something nice you can deduce if such a case arises. Okay, and that's what we want to see now. So let's write it down. So let's say you are given a Lagrangian L and your generalized coordinates are Q1, Q2, S, whatever that S is. S is the degrees of freedom you have. Okay, that's what your degrees of freedom are. Now let's say Lagrangian is not a function of let me put it this way. Okay, let's say your L is not a function of one of these coordinates. Let's call that coordinate Q of alpha. So that alpha could be 1 or 2 or whatever. So let's say one of them does not appear in L. If that is the case, then let's see what we can say from the equations of motion. So equation of motion says d over dt del L over del Q alpha dot. So I'm looking at the equation of motion corresponding to that particular alpha right now. Okay, the one which is not appearing in the Lagrangian, minus del L over del Q alpha equals 0. Okay, now if Q alpha does not appear in the Lagrangian, then this partial derivative is 0. Okay, so this guy, this term is 0, which means d over dt of del L over del Q alpha dot is 0. That's nice. It's nice because it says that if you look at this quantity, del L over del Q alpha dot, okay, if you look at this guy, then that guy remains constant. You see, I'm looking at a total time derivative here, meaning as the time changes and system evolves, things are moving around, no matter what is happening. Okay, this guy del L over del Q alpha dot, that remains a constant. Okay, so let me write it down. It says del L over del Q alpha dot is a constant. It's a constant of motion. Okay, your system is evolving, things are moving around, but the value this has does not change with time. Okay, so let me write down clearly what all I have said. I have defined already a cyclic coordinate What is a cyclic coordinate? Uh, uh, is a generalized coordinate. Coordinate that does not appear in the Lagrangian. Okay. When I say the coordinate does not appear, doesn't mean that the velocities cannot appear. The velocities can appear. Okay, so the statement about cyclic coordinate is only about the coordinate, not their respective velocities. Okay, so that's what I mean by a generalized coordinate. And we see that the moment there is a coordinate which is cyclic, you have a corresponding constant of motion. Okay, so this guy is conserved, del L over del Q alpha dot. Okay, that looks like a little abstract right now, but we can reveal what this guy is if we look at our simplest example of let's say a free particle. Okay, that's what we always do. So whenever I want to test something, I take the simplest cases, or if I want to understand something which is new to me, I take that new thing in the context of the simplest cases I already know. So I'll take this and look for a single particle in which is moving freely, so there are no forces, and let's see what is the equivalent of this guy. So I take the example of, okay, I would like to use green color if I am taking an example, and I think I can do it. Okay, looks good. Okay, so yeah, so I take a free particle and I use Cartesian coordinates. I can use Cartesian coordinates are also a set of generalized coordinates. In this case, Cartesian coordinates. Okay, I'm assuming that particle is accessing all the 3 dimensions. So what's the Lagrangian? Or maybe I should go to next. Okay, fine, no problem. So what's the Lagrangian? The Lagrangian in this case is, as you already know very well, half m x dot square plus y dot square plus z dot square. Okay, and you see that the coordinates x, y and z, they do not appear in the Lagrangian. The derivatives appear, the velocities appear, but not the coordinates. So in this case, your x, y and z are cyclic. Okay, they are cyclic coordinates or they are ignorable coordinates. Okay, which means that there has to be a constant of motion which will be del L over del Q dot, where Q will be x, y and z, all of them, all 3 of them. So let's look at what del L over del x dot is. So if I look at del L, let me go to the next. How do I go? Yes. Come on, Z. Oops. Fine. So let me look at, I want to do this. I want to calculate this thing for our case. So I should be looking at del L over del x dot and also del L over del y dot, because that is also a cyclic, y is also a cyclic coordinate, and del L over del z as well, because z is also a cyclic coordinate. And what are these? Your del L over del x dot is mx dot, right? You have x dot square, so you take derivative, you get mx dot. This will be my dot and this will be mz dot. And what is this? This is mass times x component of the velocity, right? So that's the momentum in the x direction, momentum in the y direction, and that's the momentum in the z direction. Okay. So you see that in this case of a particle moving in 3 dimensions, what is constant is the momentum. All the 3 components of momenta are constants, which you already know that the momentum is going to be conserved for this particle where there are no forces. Okay, so this leads us to define a new quantity, what we call as generalized momenta. So I will define, okay, let me make it black again. Good. So I define generalized momentum or also we call it canonical momentum or conjugate momentum as well. Let me write conjugate momentum. Okay, so I'm defining a generalized momentum or conjugate momentum corresponding to q alpha to be here del L over del q alpha dot. Okay, this q alpha could be any of the coordinates. It does not have to be a cyclic coordinate. So corresponding to every q alpha, I define del L over del q alpha dot to be the generalized momentum, and I denote it by pf alpha. Okay, that's good. And in our example for a free particle here, we have seen that the corresponding conjugate momenta are constants. Okay, they do not change with time. Okay, that's good. Let me take another example here. Okay, now let's take again a particle, and for simplicity I'll take it to be moving in 2 dimensions, and it is, let's say, also experiencing a force on it. Particle in 2D I take, so xy plane let's say, and on which you have a force which is given by a scalar potential, and this time I take the potential to depend only on y and z. Okay, sorry, I'm saying it is moving in xy direction, so let's say it is in fact, yeah, why do this? So let's say we take a particle in 3D. Okay, and we take the scalar potential to depend only on y and z. Now if this is the case, then your Lagrangian does not depend on x, right? Because it's only through the potential energy your x will appear, which means that for this case x is a cyclic coordinate or ignorable coordinate. If that is so, then something has to be a constant of motion, something has to be conserved, and that is the corresponding momentum, conjugate momentum. So let's look at what the corresponding conjugate momentum is, and it's clear what it is. It is just, you have to look at del L over del x dot. Okay, and why is it going to be conserved? For this reason which we have already seen, del L over del x. Okay, del L over del x is 0 because there is no x here, so this guy is conserved, and we have already seen what del L over del x dot is. It is mx dot. So px, the component of p in the x direction, that is conserved, But from here also you see that if I look at py, which is del L over del y dot, then that guy is not zero. That guy is not a constant, because you will see that del L over del y from here will get a contribution because of the u. Okay, and you already know that because there is a force which will act on the particle in y and z directions. Remember, the force is a gradient of potential. The momentum in y and z directions will not be constant, but in this case there is no force in the x direction. The gradient of u, the potential is not changing in the x direction, so there is no force in the x direction, and that is why the component of momentum in x direction is a constant. Okay, so this is what you also expected already in this example. Let's see a slightly non-trivial example, only slightly. Till now I've been just using Cartesian coordinates, so let's see an example where I'm using generalized coordinates. And the simplest one to think of is again that of a free particle, let's say confined to a plane, xy plane. Okay, and I use polar coordinates, and then again we see what we can say here. Another simple example, and because it's an example it has to be green. Okay, so again I take a free particle in, let's say, xy plane, and I use the polar coordinates r and theta. We already seen it that the kinetic energy is half m r dot square plus r square theta dot square. Okay, so which coordinate is a cyclic coordinate in this case? Clearly theta is not appearing here, so theta is the cyclic coordinate. Theta dot is there, but that's the velocity, that's not a coordinate. Okay, so theta is the cyclic coordinate, which means del L over del theta is 0. Okay, and you see your r is not a cyclic coordinate. R appears here, so del L over del r is not 0. Okay, good. So let's look at the conjugate momentum. Conjugate to theta, and that is del L over del theta dot, right? Let's go back. Del L over del q alpha dot. So your q alpha is theta now, so del L over del theta dot. And what is that? Del L over del theta dot. So this term is gone, gives 0. This term will give you half m times r square, and theta dot square, when you take a derivative, gives you 2 theta dot. So you get m r square theta dot. Okay, and this is a constant because of your Euler Lagrange equation. So d over dt, let me call it p theta. Okay, p theta, and your p theta is 0. Okay, or d over dt of m r square theta dot is equal to 0. Okay, we have got another we have got a constant of motion in this case, and I hope you all already recognize this quantity. What is mr square theta dot? Mr square theta dot, do you recognize this? Mr square theta dot is the angular momentum. Okay, the angular momentum of a particle which is not acted upon by any torque will be constant. Okay, and that is what you see here. So this is nice. We In this case, the quantities are very familiar, but even if, let's say, we are looking at a system which we have very crazy kinds of generalized coordinates, all I have to do is always first start by searching for the coordinates which are cyclic. Okay, you just see which one does not appear in the Lagrangian. Once you have found it, you already know that whatever is happening to the system, whichever way things are moving around, there has to be a corresponding conjugate momentum that will be conserved. Okay, and that's a nice thing to know. Okay, that's nice. Okay, let's make a summary of what we have said, and I'll make some observations based on that. Okay. So in the three examples that I have taken, I have seen that in the example number 1, where I had a free particle moving in 3 dimensions, I had px, py, and pz. They were all constants. Okay, and px, I wanted to write it this way: mx dot is equal to constant, my dot is equal to a constant, mz dot is equal to a constant. Okay, that's what we saw in the first example. And then I had a particle which was in a potential which didn't depend on x, and I saw that mx dot was a constant in that case. Okay, and then we looked at the example of again a particle in 2 dimensions but using polar coordinates, and we saw that mr square theta dot was a constant. Okay, now note all these equations that I have written down here: mx dot constant, mr square theta dot constant, they are all first order differential equations. Okay, there is only one time derivative involved, theta dot or x dot or y dot or z dot. Okay, and these equations I have not obtained, these first order differential equations I have not obtained by solving the system first. It's not that I have solved for the system, found where how things are evolving with time, where how q alpha, okay, where alpha runs from 1 to whatever degrees of freedom you have. I have found the time dependence of q alpha, and then found by taking a derivative of this q alpha these equations. That's not what I have done. What I have done is looked at which coordinates are cyclic and immediately written down these first order differential equations. Okay, and usually these are the things which are much more informative because they immediately tell you something about the system. So you are not always very much interested in knowing where each particle is going. Okay, that will be of course useful and you have the full information, but that may not necessarily be very interesting thing to know. What may be more interesting thing to know is, for example, that the angular momentum is conserved in this case, or the momentum is conserved, or some such quantities are conserved. Okay, and those you can immediately get. And these first order differential equations, let me write down, these are first order differential equations. Okay, and these first order differential equations are called first integrals of motion. Okay, that's what they are called, first integrals of motion. And in general, if you are looking at a system of s degrees of freedom, you would have the first integrals of the following form: the first integral of motion will have the form, of course it can involve only first order time derivative, so it will be some function f. Okay, like here it depends on the coordinate r, okay, and first time derivative of theta. So it would be in general a function of the coordinates. Let's say the system has s degrees of freedom, and then it will involve the first derivatives, first order derivatives, and possibly time, and this will be a constant. Okay, that's where we will stop today, and I hope you realize that having first integrals of motion is a very useful thing. Okay, you immediately get some good piece of understanding about your system. Okay, we'll continue from here in the next video. See you then.